and welcome to this first tutorial on beams. Since this is our first tutorial, we'll have to discuss a few fundamental things. After drawing our free body diagram and finding reactions, we will discuss sign convention. We will then go on to developing our axial, shear and bending moment diagrams before discussing some tips on how to identify if we're correct. So let's use this beam here to demonstrate all of this. Let's get cracking. Let's start off by drawing a free body diagram and finding the reactions. So looking at this beam, at A, I have a pin support, which means there'll be two reactions, one in the vertical and one in the horizontal direction. And at D, I have a roller support, meaning that there will be one reaction in the vertical direction. So let's replace these supports with the reaction forces. So here at A, I'll have AY and AX, and here at D, I will have dy. So now that I have my free body diagram, I can see that I have three reaction forces that I need to find, and I know that I have three equations of equilibrium in 2D, meaning that I can find these reactions. So let's start off with that. Before I find the reactions though, I need to agree on my positive sign convention, which looks like this. I'm going to start off with the sum of forces in X, because that is the simplest. I've already identified that there are no horizontal forces in the X direction. So in X, I have the reaction force AX plus nothing else, so this equals 0. I'll move on now to do the sum of moments around A. And if I do that and I start at D, I can see that I have, this is my positive direction, dy contributing a positive moment times a perpendicular distance of 9 between the line of action of dy and point A. And I've got 60 at C contributing a negative moment around A times a distance of 6. And I've got the 120 also contributing a negative moment times a distance of 3. And that equals 0. If I sum this up and isolate dy, I'll find that 9 dy equals 720, and therefore dy equals 80 kilonewtons. And once I know what dy is, I can pretty easily do my sum of forces in the y direction, and with that being my positive direction, I can see that ay plus dy minus 120 and minus 60 equals 0, and therefore ay, which I'm looking for, equals 120 plus 60 minus dy. I know that dy is 80, and therefore ay works out as 100 kilonewtons. And now what I can do is replace the variables in the free body diagram with the actual values that I found. So starting off with AX, we found out that that was 0, so get rid of that. dy came out as positive 80, so the direction I assumed is correct, and I can put 80 kilonewtons here. And AY came out as positive 100, so that means the direction I assumed here is also correct, and that gives me 100 kilonewtons here. It would also be prudent to actually check the reaction forces, but I'll leave that up to you. Now, before I go on to look at my internal forces, I do need to decide on a sign convention. I discussed this in much more detail in the lecture, so we will just look at the conclusions that we arrived at in the lecture. Okay, and this is how we will proceed. So let's look at this sign convention. I've taken out a teeny little bit of this beam to demonstrate. I'm first going to look at my sign convention for axial force. And just like I did with trusses, I am going to assume that axial force in tension is positive. Now remember, these are all internal forces, right? So when I close these little bits of the beam together, all these internal forces have to disappear. So I can see here that they are of the same value, and they are opposing each other in direction, and so when I close this up, they'll disappear. Let's now look at my shear force. So in my sign convention, my shear force, when I cut this bit of the beam, creates a positive moment according to the right-hand sign convention. And therefore, this will be my positive shear, and it follows that as I move further on to the right, this will have to balance the shear out. And the last thing I have is my moment. And once again, I'm going to take a positive moment when I look from the left according to the right hand rule, and then these follow on. So this will be the positive sign convention that I use in this exercise. So now that we've discussed the sign convention that we're going to use, which I'm going to remind you is a man-made thing, so there's no right or wrong, but whatever sign convention you choose or you've been taught, you need to be consistent. We'll move on to discuss where we're going to look at the beam. So what are the important places for me to consider when I am looking at internal forces? Let's have a look together. We will always cut the beam where there are places of interest. So that could be after a force is added, where there's a UDL or a distributed load, or after and before supports. So if I look at this beam here, I can see that I've got a supporter A, okay, and then there's kind of nothing really happening between A and B. So I'll cut somewhere between A and B to figure out what the internal force is there. Afterwards, at B, there is an external concentrated load applied. So I will need to check what the influence of that load is on the internal forces. So I'll also cut somewhere between B and C. And then again, there's another force applied at C. So I will cut somewhere between C and D. Now, before I start looking at the cuts and creating my diagrams, what I like to do is I like to draw under my free body diagram places for my axial, shear, and bending moment diagram. And I also like just to take down places that will be of interest. So at the support, where the concentrated load is added, and at the end support, because I know that I'll probably want to have a look at what happens to the internal forces there. And now that I've done all of that preparation, I am finally ready to look at the internal forces in the beam. So let's start off with segment AB. First thing I'll do is I'm going to draw the bit of beam somewhere, stopping somewhere between A and B. I am going to put on any forces, reaction forces or external forces that I have. In this case, I just have that reaction force of 100. And now I am going to place all of my forces. So I'm going to have N. I am going to have S, the shear force, in the direction that we agreed. And I am going to have my bending moment. So I'm just drawing these all initially in the directions according to the sign convention we just agreed on. Now, in segment AB, I'm obviously going to be looking from A until B. So I'm going to call that distance x1, and x1 is going to be between 0 where I start and up until 3, just where I hit that new concentrated load. So all we have to do now is write 3 equations of equilibrium to find out these internal forces. We'll start off with the sum of forces in x equals 0. And in this case, I've got my n x and nothing else, so that works out as 0. I'm just writing this subscript 1 just because it's my first cut and I want to differentiate from any forces that I'll find and their function potentially of x1 of this distance. My next thing that I'm going to do is my sum of forces in the y direction equals 0. And in this case, I've got 100 going up, so in the positive y, and minus S1 going down. And so S1 works out as 100 kilonewtons. And the last thing that I'm going to do is I am going to do my sum of moments. And I always do the sum of moments around the cut. So always kind of at this point here where I'm cutting the beam. So I'm just going to call that sum of moments around the cut. And here I've got the moment, okay, so m1, which is a function of x1, it's giving me a positive moment. It's already a moment, so I don't need to multiply it by anything. And then the 100 gives me a negative moment around the cut, so minus 100, and its distance is going to be x1. So this distance will vary depending where I am on this segment between A and B. It can be at half a meter, at a meter, at 2 meters, and right up until I reach B at 3 meters. And that means that my moment, m1, x1, is 100 times x1. Now this is my equation, so let's highlight my equation, and we'll see later on in this series why equations are important. But what I want to do now is I want to figure out where is it important to just check what the moment is. So I am going to check what the moment is. So what is m1 when x1 equals 0, so right at the support, and what is m1 when x1 equals 3 meters, so at point B. These are two places that I think are important to check. I could check what happens anywhere along the way though with this. So if I substitute x1 with 0, I get 0 here, and if I substitute x1 with 3 meters, I get 300 kilonewton meters. I can see that this is a linear line, so I know that I am going to be going from 0 to 300 in a straight line. The other thing that I need to consider with a moment is where I draw it. So I can draw my moment here on this side of the beam, or I can draw my moment here on this side of the beam. When we look at this in the UK, it is pretty important for us to always draw this on the tension side. And there are reasons to it, and I do discuss this in the lecture, but drawing on the tension side, in short, gives me a very good indication of where I would reinforce concrete, for example, and it gives me a good indication of the deflections of the beam. Both things pretty important when it comes to design. So let's just discuss what that means in terms of what I need to draw. So I'm going to just draw out my little cutoff of the beam, right? I assumed that my bending moment was in this direction, right? That was my assumption. It came out positive, so indeed it is in this direction. And what I can see is that this direction of moment pulls the bottom bit of the beam and pushes the top bit of the beam. I can see this, for example, as a coupled force. I can just see that this arrow pulls the bottom and pushes the top. Now, if it pulls out the bottom, it's making it longer, so that is in tension. And if it's pushing the top, it's making it shorter, so that is in compression. And that means that here, from at 0, it's at 0 here. But when I get to this point here, when I have my 300, it is positive, which means that tension is on the bottom. So I'm going to draw that on the bottom. So let's actually just start by drawing out my moment diagram, since I've discussed that so much now. So I am going to give 300 kilonewton meters here. As I said, I'm drawing it on the bottom because the bottom is in tension, and that's what I do in my sign convention. And I go from 0 to 300, and I can see that this is plus. If I go back to draw my shear, I got that my shear was 100 kilonewtons plus, so I can just go up here and I see that I have a straight line right until here, and that is 100 kilonewtons, and that is a plus. And although I got 0 for my axial force diagram, whenever you're asked to draw something, do always draw it. So I just have 0 here. And that was my first cut and my first part of the diagrams. So I hope that the first segment, AB, is clear. We did go over quite a lot of things, so let's do the next cut and go over them again. Okay, so moving on to segment BC. Just like before, I'm going to draw it out. Now I am going to draw it out from the start. We'll see as we progress through these, we'll see that there are shortcuts that we can make. But just for now, we're going to look from the beginning. So I've got 3 meters that I already know everything about. And then I have from here my x2 starting. So x2 is going to be between 0, because it starts from here, it'll be from 0 to 3 meters again. I am going to draw in all my forces, so I've got my 100 reaction. I've now passed point B, so now I've got 120 of external force here. And between B and C, I also have my internal forces. So I've got N2, so just my second axial force. I've got S2 and I've got M2. Again, all of these drawn according to my sign convention. And now what I need to do, I need to just go on through the forces and write out. So sum of forces in X equals 0. I've got N2 and nothing else, so N2 equals 0. If I move on to doing my sum of forces in the Y direction, I've got 100 going up, then I've got 120 going down, and then I've also got S2 going down. And so if I isolate S2, I can see that I get minus 20. And my very last thing is my bending moment. Once again, I'm doing it around this new cut. And starting from A, I have got a minus from the 100, okay, creating a negative moment, times 3 plus x2. So that is the total distance until the cut. And then I've got a positive moment from the 120 times x2. And I've also got m2 giving me a positive moment here. Once again, I need to isolate the moment. And if I do, I get that m2 equals 100 times 3 plus x2 minus 120 x2. And just to make this nice and easy, I can open the brackets. So I've got 300, and then I've got plus 100 times x2 minus 120 x2, so that works out as 300 minus 20 x2. Okay, and that is my equation for moment. Once again, let's check what happens at some interesting points. So I want to know what happens exactly at point B, so when x2 equals 0, and I also want to know what happens when x2 equals 3 meters. So essentially I'm at point C. So when x2 equals 0, I get 300 kilonewton meters. And when x2 equals 3, I get 300 minus 20 times 3, so that gives me 240 kilonewton meters. Now the 300 makes me very happy because I see that I ended at point B from my previous segment at 300. I have 300 again, so there's no jump, which is exactly what I'm expecting. So now let's draw everything in. Let's start with the axial force. Once again, I've got 0 here, so just draw that out. In terms of my shear, I have now minus 20, so it means that I jump down here to minus 20. And this is really good because I can see that where the concentrated load of 120 was, I have this jump in exactly that value, and that is exactly what I'm expecting. So that is great. It means that I'm on the right track. And here I start off with 300 and I end with 240, so somewhere here. Once again, let's just quickly chat on why I've drawn this on the bottom. So once again, we assumed that our bending moment looked like that. So pulling at the bottom and pushing at the top. So tension at the bottom and compression at the top. It worked out positive. So I know that this is the right direction, means tension's on the bottom, and I draw my bending moment diagram on the tension side. Okay, let's look at our last cut of the day. So segment CD, and once again, let's draw this out. Now I am going to start from point A. There are shortcuts, as I mentioned before, and we will get to them. But as a first tutorial, let's do this all the long way there. So drawing out all my beam, I've got 3 meters that I've passed. I've got another 3 meters that I've passed. And here starts my X3. With X3 being from 0 to 3 meters again. I'll draw in my forces, starting off with the reaction of 100A, my 120 kilonewton of external force, and also now that I've passed my 60 kilonewtons, drawing that in as well. I'll draw my internal forces, my axial force, my shear force, and my bending moment, all in the directions that we've already agreed on. And once again, we will move on to writing our equations. So starting off with the sum of forces in the x direction, I only have N3 here, so once again the axial force equals 0. Moving on to my shear force, I have 100 going up, minus 120, and minus 60, and also minus S3. If I isolate S3, I will find out that S3 equals minus 80 kilonewtons. And my very last thing is going to be the sum of moments at the place where I do my cut again. And now I've got minus 100 times 6 plus x3 plus 120 times 3 plus x3 plus 60 times x3 and plus m3. If I isolate m3, I am going to get 100 times 6 plus x3 minus 123 plus x3 and minus 60 times x3. Let's open the brackets and write that out a bit more neatly. So I've got 240 minus 80 times x3. And just like before, we're going to look at some points of interest. So initially, I would like to look at what happens when x3 equals 0, meaning I'm exactly at point C, and what happens when x3 equals 3, which means I'm at the other support, I'm at D. Now I am going to hope that when x3 equals 0, so I'm at point C, I get plus 240, right, because there's no jump there. And when I arrive at D and I'm at the very end of my beam at that support, that roll support, that I get 0. So let's check it out. When x3 equals 0, I do indeed get 240 kilonewton meters. Brilliant. When x3 equals 3, I get 0. So these are two things that I'm expecting to get, and they give me a good indication that I have calculated everything correctly. So let's put everything on this graph and finish finding all the internal forces. So once again, 0 for axial force. In terms of S3, I have minus 80. So I need to go down here to minus 80. And this little jump from 20 to 80 gives me 60, which is exactly that external force. So that is really good. I go down from 240 to 0 to my support. And that obviously all worked out as plus in the meanwhile. Once again, with a moment, I assumed that tension was at the bottom. My results started off as positive and then went to 0, meaning that the direction I assumed was correct, meaning that tension was at the bottom of the beam, and therefore I drew this at the bottom of the beam. So this is a final look at our diagrams. We can see here that the axial force is 0 throughout. We can see here that the shear force diagram is straight lines between point loads and jumps when a concentrated load is added, and that jump is the same value as the concentrated load. And we can see here in the bending moment diagram that the addition of each of these loads changes the slope of the bending moment diagram. The other interesting thing that we can see is that when the shear crosses 0, we get a minimum or maximum moment. And there is a reason behind all of this that we will discuss later on. But for now, we have found all the internal forces required in the beam, and this is the start for actually designing beams. And that is how you solve and find the internal forces in a beam. This was quite a slow and very systematic approach, but I hope that's helped you figure it out, and join me when we do some more complicated force loads and we also look at some shortcuts. Thanks for joining me. Bye for now.